Hello my dear students, I warmly welcome you to Sia's digital classes. In this lecture, we are going to discuss about one of the important theorem from the permutations. So let's see the statement of the theorem first of all. Define alternating group of degree n. Prove that an alternating group A suffix n has order n factorial by 2 for n value greater than 1. Okay. So here alternating group, we have to define the definition of the alternating group, and at the same time we have to find out the order of that alternating group is equal to n factorial by 2. In the previous lectures we clearly discussed that S suffix n is the symmetric group. Okay, symmetric group with order n factorial, because if the suffix value is n, then it will become n factorial. Suffix value 7 factorial, suffix value 3 factorial, based on that. Now apart from symmetric group, now we are going to define the alternating group. So let's see the definition. First of all, what is the alternating group? Alternating group, so the group of even permutations. Okay, in a group there exists to even permutation and odd permutation, but here especially we are taking that the group of even permutations, okay, of n symbols. N symbols and you can write set in this format, flower bracket 1 2 3 up to so on small n. Okay, the group of even permutations of n symbols are the group of even permutations of a finite set is called alternating group of degree small n. Okay, so ఈ సెట్ లో మనకు ఎన్ని ఎలిమెంట్స్ ఉంటే అన్ని ఎలిమెంట్ మనం కౌంట్ చేస్తే సో we will get that the order of that alternating group. So mathematically this group is denoted by a suffix n. This is the definition. We are counting only even permutation. Okay, there also exists odd permutation in that group, but we are counting only the even permutation. That number gives the order of the alternating group. So let S suffix n. Now we are entering into the proof. We have to prove that alternating group has an order n factorial by 2. So to prove that alternating group, so we have to take the symmetric group. Let S suffix n is equal to small e1 e2 up to so on e suffix m, o1 o2 up to so on o suffix n be the symmetric group of even and odd permutation. Okay, so here e is nothing but even, not an identity element. Okay, e is represents that even permutation, and here o represents that odd permutations. Now the order of this symmetric group you can write here. We have two types of permutation. So the m represents the even permutations and n represents the odd permutation. By together,ing them, m plus n is equal to we have n factorial. That is, we are writing in the equation format. Mod Sn is equal to m plus n is equal to n factorial. That is equation number 1, where I am clearly mentioning that small e1 e2 up to so on e suffix m are small m permutations. Okay, even permutations, and o1 o2 up to so on o suffix n are small n number of odd permutations. Okay, this is the given data. Okay, so we are writing from the statement. Let I'm taking that let capital small t be a transposition. Okay, small t be a transposition in the symmetric group S suffix n. Okay, so what is the transposition? In the previous lectures we discussed that the definition of the transposition. The length of any cycle is equal to 2. Okay, length of any cycle is equal to 2, then it is called a transposition. Okay, the basic format is you can write in this format, pair of a comma b. Okay, pair of 1 comma 2 or cycle of 1 comma 2. So that cycle having length 2, length means the total number of the elements in that cycle is equal to 2, then that is called length. Length of the cycle is equal to 2. Those types of cycles are called transpositions. So alanti oka transposition I am taking it as t. Okay, t be a transposition in S suffix n. Since S suffix n is a group, in the previous lecture we proved this condition, and the same time S suffix n is not an abelian group. Why? Because it is not satisfying the commutative property. So S suffix n is a group, then closure property holds in S suffix n under addition modulo, under multiplication. Sorry. So that is for E1, E2 up to son E suffix m, O1, O2 up to son O suffix n belongs to S suffix n. We are going to prove the closure property. So to prove the closure property, so you have to take the elements first of all in that set. I am taking these two elements E1, E2, Em, O1, O2, On are the two elements. Then and small t is the one transposition belongs to S suffix n. Now for this t and these two elements we have to make the multiplication property. Okay, so then you will get t into E1, t into E2 up to so on t into E1, and t into O1, t into O2 up to so on t into O suffix n belongs to S suffix n. Why? Because that is also exist in the permutation formats. Okay, it is not a number. The product value also will exist in the permutation format. So then the permutation format represents the symmetric group. That is only we are writing belongs to S suffix n. And since t is a transposition, transposition is nothing but you can write in this format pair. Okay, so in the form of open interval or in the form of cycle, and it is an odd permutation. Okay, it is correct only. Why? Because if you write one pair, you can count it is a 1. If you write two pairs, you can count them as two cycles are there. If you write only one cycle, the number of cycles is 1. 1 is the odd number. So therefore t is a odd permutation. Then t into E1, t into E2 up to so on t into Em are also odd permutation. Why? Because E1, E2 up to so on Em. Okay, we take in E1, E2 up to so on Em are the even permutation. For that even permutation, if you add one more element, one more transposition, then even numbers will become odd numbers. Okay, for example, here you have E1 is equal to 1, 2 and 2, 3. This is the E1 first permutation. For this permutation, if you add t, okay, 3, 4, then the total number of the cycles will become 3. 3 is an odd permutation. Okay, so whenever you multiply with te1, you will get the odd number of permutation. That's why they are mentioning that for the even permutations, if you multiply with the transposition, then you will get the odd permutations. And at the same time, for the odd permutations, if you multiply the transposition, then odd permutations will become the even permutations. Okay, that is the vice versa relation. So now from those permutations, okay, from the set, I can take let t into e suffix I is equal to t into e suffix j. I am taking one condition. Okay, for out of these two odd permutations, I am taking one condition t into e suffix I is equal to t into e suffix j. Okay, for I value less than or equal to small m, j value also less than or equal to small m, where small m represents the even number of permutations. Okay, don't forget that value. You have to mention this sign. I less than or equal to m and j less than or equal to m. Then by left cancellation law, if you cancel this t on both sides by left cancellation law, okay, then you can write e suffix I is equal to e suffix j. Since s suffix n is a group and we are getting two elements are equal, okay, those are not elements, those are the permutations. If you get the two permutations are equal, then the counting will affect on the order of the symmetric group. Okay, we are taking first of all those are the different permutations. We have each and every permutation is different, but we are getting we have two permutations, those are equal. Then the order, that number will affect on the order of the symmetric group. So therefore, since Sn is a group, then e suffix ej is a absurd. Absurd means it is a contradiction or it is a meaningless. So therefore, definitely what we have taken this condition, okay, t into e suffix I is equal to t into e suffix j is wrong. So therefore, definitely t into e suffix I not is equal to t into e suffix j is the correct one only. Whenever you write these two values are not equal, then what is that meaning? The small m permutations. Okay, what are the small m permutation? Even permutations. Okay, small m permutations are different. Why? Because we are showing that those are not equal. Those all are different means exactly small m even number of permutations will be there and exactly small m odd permutations also exist. So therefore, I can write the relation between even permutation and odd permutation as m less than or equal to n. Why? Because I am taking first even permutation, so therefore m is the even number and n is the odd number. M less than or equal to n. That is the taken equation number 2. Similarly, whenever you write this condition, at the same time odd permutations also different permutations, okay, and distinct permutations. So therefore, there are small m even permutations, those also distinct. So then I am writing n less than or equal to m. That is taken as equation number 3. From equation number 2 and equation number 3, m less than or equal to n less than or equal to m, you can write m is equal to n. Okay, one of the noun property in the sets theory. A subset are equal to b and b subset are equal to a, then you can write a is equal to b. From that condition, n is equal to m, where what is the m and n? Those are the even permutation. M represents the even permutation, n represents the odd permutation. Both are equal. So therefore, then by equation number 1, we can write m is equal to n is equal to n factorial by 2. If you write m is equal to n, okay, so m plus m is equal to 2m. That 2m is equal to n factorial. Then m is equal to n factorial by 2. Or else if you take n is equal to m, n plus n is equal to 2n. 2n is equal to n factorial by 2. So therefore, n is equal to n factorial by 2. So in this format, you can write m is equal to n is equal to n factorial by 2. Where I am writing m represents the total number of the even permutation and n represents the total number of the odd permutation, that is equal to n factorial by 2. So therefore, clearly we can say that there are equal number of even and odd permutations. Now our concept is nothing but here we got even total number of even permutation. How much that number is? N factorial by 2. According to the definition of the alternating group, what is the definition? The total number of the even permutation. So therefore now I am matching both of them. Even the total number of the even permutation is equal to the order of the alternating group. So therefore A suffix n be the alternating group. Okay, alternating group is nothing but even permutation. Even permutation total number. So therefore having degree n. So therefore order of mod A suffix n means that order of alternating group is equal to total number of the even permutations. Okay, that is n factorial by 2. I am writing directly. So therefore the alternating group A suffix n has order n factorial by 2. Already n factorial is nothing but order of the symmetric group. Okay, order of the symmetric group is n factorial. In the symmetric group, half of the elements, okay, half of the elements nothing but half of the elements belongs to even permutation. So that is you can take n factorial by 2. Remaining n factorial by 2 is odd permutation. You will mix up them, again you will get the same value only, n factorial by 2, n factorial by, so 2 by 2 you will get again n factorial. Okay, this half part represents that even, this half part represents that odd. Okay, so this is the proof of the an alternating group has order n factorial by 2 for n greater than 1. Okay, I hope you understood this theorem very well. In the next lecture we are coming with another important topic. So make a perfect practice, prepare well. Until bye, thank you.